Okie dokie, chemists, let's get started. Thank you for joining me on this Turkey Day or Turkey Week mini lecture. Plan is to get through the rest of intermolecular forces in chapter 11, and then that's a good place to stop. And then we'll switch over and do some cumulative final exam review. So the plan is to get to slide 20 in these chapter 11 slides, and then we will do review. Okay. All right, so let's just prime ourselves with what we're talking about, and that is intermolecular forces. So intermolecular forces are attractions between molecules. And so the attractions that happen between molecules depend on what that molecule actually looks like. So, you know, whether the molecule is big or small, whether the molecule is polar or nonpolar. So those ideas back in chapters 8 and 9 are going to come back in this chapter as well. And so just to kind of relate to this, chapters 8 and 9, we looked at chemical bonding that make up an actual molecule. So no longer are we talking about covalent bonds. We're not talking about ionic bonds. We are looking at, okay, how does one water molecule interact with another water molecule nearby? While in chapters 8 and 9, we looked at, how are hydrogen and oxygen bonded to one another in one oxygen or water molecule. So the whole idea here is that intermolecular forces are attractions between molecules. What we're looking for are these attractions between partial charges in molecules. So there's different ways we can create these partial charges, and that gives us our different intermolecular forces that we'll talk about here. There's 4 different ones, and so each of these I kind of have like summarized what kind of criteria are you looking for each of these different types of IMFs. So the first one that we looked at here are London dispersion forces. So I went over the slide, but I'm just reviewing. London dispersion is an attraction between all types of matter. And how we get London dispersion is the idea that electrons are always moving around, and at some point in time, you might just have a temporary dipole be produced, where we're looking, I think we looked at this picture over here. At one specific point in time, you may just have more electron density on one side of your atom than the other. And so what happens there is you produce this partial separation of charges just for a moment. And so just at that moment when these 2 electrons that are zipping around this atom end up on this side of this atom, a nearby atom might be attracted to either the partial negative or partial positive side. And so this last picture, what you're seeing is this instantaneous dipole attraction, where just at this moment of time where we have an unequal spacing of our electron density, we have this momentary attraction between 2 atoms because electrons are just whipping around one another. And so this attraction is very, very weak because it only happens, once in a while. It's temporary. It forms, this attraction forms, but then it goes away the next second. And so what we see is that London dispersion forces, that attraction increases when the number of electrons increase in a substance. If there's more electrons present, there's more likelihood that you can have an unbalance of electron density in your atom. So what we're looking for is as molar mass increases in your substance, because as our molar mass increases for our elements, yes, the mass increases, but what also increases when we, go down the periodic table? The number of electrons. And so more electrons, more chances for London dispersion to happen, all right? So these are temporary dipoles that happen. Okay. So a little bit more about London dispersion. Since we're just looking at electrons here, all matter has electrons, so everything has London dispersion attractions, but it's going to be really important in nonpolar substances, what we're going to find. Because when we start working with polar substances, other stronger intermolecular forces take over, but when you're working with a nonpolar substance, London dispersion is the only IMF that's present. So it's really important for nonpolar things. Atoms also, all right? Because atoms are nonpolar. Okay, so why London dispersion happens, and this idea that electrons are moving around lends itself to the idea of this concept of polarizability, ease in which an electron cloud can be distorted. And so that is related to those temporary dipoles that are created when talking about London dispersion forces. So the idea that weight increases, the number of electron increases, the more likelihood London dispersion will happen. So that's one of the criteria for London dispersion. But another idea of London dispersion also is surface area. If there's a lot of surface area in your molecule, what we'll see is that London dispersion attractions also happens a lot. So there's actually two criteria here for London dispersion, as molar mass increases, but also as surface area of your molecule increases. And here's an example. All right, so here are two isomers. This is N-pentane, where all the carbons are like in a straight chain. All five. All 5 carbons are in a straight chain. And then here's neopentane, and this molecule puts all the carbons like bonded to one another. So what we see here for neopentane and N-pentane is that they have the same chemical formulas. So therefore, they should have the same molar masses. They weigh the same. So according to London dispersion, if they weigh the same, then they should have the same amount of London dispersion forces. But what we actually see here is that their boiling point temperatures are different, that it is harder to boil N-pentane. And so boiling point temperature is an indication of the extent of intermolecular forces present. So what we see here is that because N-pentane is a long, skinny molecule, it has a lot of surface area, has a lot more surface area than our more spherical neopentane, that N-pentane actually has more IMFs present, has more IMFs in the form of London dispersion forces because of its increased surface area. So what we see is that linear molecules will actually have more London dispersion than spherical molecules, or kind of more compact particles. And this is really important when you're looking at two molecules that are basically the same weight. So then you kind of go to the next step and look at surface area. And so I kind of hinted at this idea of boiling point temperature telling us something about IMFs. So let's think about this. When we boil a liquid, let's say we're boiling water, right? When we boil water, we turn what? I guess I already said it, liquid water into gaseous water, right? So when we do that, when we turn a liquid to a gas, what are we breaking when we boil water? Do we break the covalent bonds between the oxygens and the hydrogens? No, or what are we breaking? What are we breaking? The IMFs, what exactly we're talking about here, yeah. So since we're breaking IMFs, if we know the boiling point temperature of substances and we compare boiling point temperatures, what that tells us is the general amount or magnitude of IMFs that are present. The higher the boiling point temperature of a substance, the harder it is to break those IMFs. Higher boiling point means that there's more IMFs present. All right, so that's a really good indication of just a way we can measure the extent of intermolecular forces that are present for a substance. So here are some examples, like if you look at neon, argon, krypton, xenon, you can see the boiling point temperature increase. And if you look at the periodic table, you know that those atoms, they get heavier as you go down the periodic table. So we see that helium, neon, argon, krypton, that those boiling point temperatures increase because their weights increase, and this is due to the increasing amount of London dispersion forces there. And then you see the same thing for the halogen series as well. Diatomic fluorine, chlorine, bromine, iodine. Also, we're going down that group. Atoms are getting heavier, but these molecules are getting heavier, more London dispersion as we go down, all right? Okay, so that is London dispersion. It's present in all matter, but it's especially important in nonpolar compounds. Okay, so let's look at some other examples. All right, so remember, boiling point temperature is a good indication of IMFs. All right, so let's look at this boiling point data of these 4 molecules. So we have 230 Kelvin, 250 Kelvin, 290 Kelvin, 350 Kelvin. So we see, oh, okay, boiling point temperature is increasing as we go left to right. Okay, so relating to what we understand about how intermolecular forces and boiling point temperatures are related, does London dispersion explain why we see a difference in boiling point temperatures here. Let's look at the molar masses of these compounds. I give it to you. So it looks like this compound is 40 AMU, 46, 44, 41. No, yeah. So what we see here are that these weights, are they really that different? Are these atomic weights different? No, they're all basically the same. But are the boiling point temperatures different? Heck yeah, they are. So it looks like London dispersion forces is not fully explaining these boiling point temperature differences that we're seeing. All of the weights are basically the same. So we would anticipate all the boiling point temperatures would be the same, but they're not. And so this is what lends ourselves to the next type of IMF that takes over. The reason that these boiling point temperatures are different is because some of these molecules are polar. Polar molecules have permanent dipole moments, which will create stronger intermolecular forces, all right? So we will look at the next one, which is dipole-dipole interactions. So the thing you want to look for dipole-dipole interactions are things with permanent dipole moments, molecules with permanent dipole moments. Basically meaning, is it a polar molecule or not? Polar molecules have permanent dipole moments, and so you can think of them as like little magnets that are attracted to one another. And so if you want to boil that substance, you got to give a lot more energy to rip those little magnets apart, right? So permanent dipoles are absolutely stronger than those temporary dipoles we talked about in London dispersion forces, all right? So, and that is what explains the difference in this trend. Propane is the only non-polar molecule in this series, but we see, ether, this aldehyde, and acetonitrile are very polar molecules. You can tell by the dipole moment that's given here, mu. That dipole moment is increasing in this trend, and that is what is explaining our boiling point temperature difference. So how do polar molecules produce these dipole-dipole interactions? So remember, we talked about polar molecules. If a molecule is polar, we have a permanent dipole that's present. So basically, you have a place on your molecule that is permanently partially negative and another part that is permanently partially positive. And so that means a neighboring molecule that also has a partial negative and partial positive can be attracted to one another all the time. This attraction doesn't go away because it's not temporary like we talked about LDF. These are permanent. So you're looking for molecules with permanent dipole moments, meaning you're looking for polar molecules. They're like little magnets that are attracted to one another. Right? I like to think of it like this. This attraction is called dipole-dipole interaction, which means you have to have one dipole, a permanent dipole, attracted to another permanent dipole. Two things with dipoles, permanent dipoles, attracted to one another. So kind of the name implies what has to be present. All right, so let's look at some examples. So let's look at example 1. So I have some compounds, fluorine, argon, HCl, and H2S. So here are the molar masses of these, okay, just generally. So if you look at these molar masses, are they really that different? No, they're all kind of the same. They're very similar, in a very similar range. So let's see what differences we can kind of bring out, because what we see here are very different boiling point temperatures. F2 has a very, very low boiling point temperature, while H2S has a much higher boiling, it's pretty cold still, but it's a much higher boiling point temperature. So fluorine, is this a polar or non-polar compound? I hope you can tell me without actually even having to draw it. Can you tell me? It's non-polar, yeah. It doesn't, you don't even have to draw the Lewis structure. You know that fluorine is bonded to another fluorine. Those electronegativity differences will cancel each other out. It'll be nonpolar. All right, argon, polar or nonpolar? It's just an atom. Don't think about it too hard. It's nonpolar, yes. It's just an atom. There's no electronegativity difference. All right, HCl. Polar, yeah, because again, a bond, HCl attached, an H attached to a Cl, different electronegativity difference. We just have to know they're different. We don't need to know the extent, but yes, that is polar. And then finally, H2S. So this one you might actually have to draw. So sulfur Here's the trick though, sulfur is in the same group as oxygen, so H2S is going to look exactly like H2O, like water, except instead sulfur is going to be in the center. So sulfur, 2 hydrogens, 2 lone pairs. But if you do the 6 steps, you'll get the same thing, right? Okay, so then the question is H2S polar or nonpolar? It is polar, but doesn't it look like these lone pairs and these bonds cancel each other out? Yeah, it does. But what's wrong with H2S? Is H2S flat? No, just like water. Is water, is water linear? No, it's not. When we draw the Lewis structure this way, we have to understand the electron geometry is tetrahedral. It's tetrahedral, so what this actually looks like is a bent molecule. Although this, Lewis structure is correct, we can draw it this way that shows, oh, those hydrogens are in a bent arrangement, and then this is in fact a polar molecule. Okay, so this first example, do these molar masses explain the large differences in boiling point temperatures? Here, do those molar masses? No, those molar masses, they're all basically the same. So LDF does not explain the differences here, but what does explain the difference is polarity. The nonpolar compounds have very low boiling point temperatures, and then the polar compounds have slightly higher boiling point temperatures, less negative boiling point temperatures. Okay. All right, so let's do another example. Let's look at acetone and butane, and this time I drew the molecules for you and kind of made it obvious the criteria that is here. All right, so the molar mass of acetone and butane, they're the exact same, about 58 grams per mole, those molar masses. So you would think, oh, the boiling point temperatures would be similar, but they're not. And again, this is because we're applying the idea of dipole-dipole interactions in addition to London dispersion. So if we think about the IMFs that are present in an acetone molecule, it will have London dispersion because all matter has London dispersion. But what other IMF is present in this acetone molecule? And I try to make it obvious in the picture. It also has dipole-dipole attractions. Yeah, because we have this oxygen that's messing up the symmetry. We have partial negative and positive on this molecule. All right, what about butane? Does butane have London dispersion? Yes, because everything does. But does butane have dipole-dipole? No dipole-dipole, yeah, none. So that is that difference, the lack of dipole-dipole in butane explains that lower boiling point temperature difference because no dipole-dipole. They both weigh the same, but one's polar, one's nonpolar. So we see a big difference in boiling point temperature. Okay, so let's look at some more examples. All right, so I hope you recognize by now that boiling point temperature is a really good indication of the magnitude of intermolecular forces that are present in a sample. But we're only 2 out of 4 through our way through the list, right? There's 4 intermolecular forces, so we still have 2 more to go. So let's look at this idea. Okay, boiling point temperature, good indication of IMFs in a sample. So as IMFs increase in a sample, usually what we see is a higher boiling point temperature. And so we talked about molar mass a lot. Usually as the weight of something increases, IMFs increase, so what we see is boiling point temperature increase. So if you look at this graph shows boiling point temperatures of different compounds in the same group. So if we look here at carbon, silicon, germanium, tin, with hydrogens attached to it, we see that, oh, this trend definitely follows that idea. As molar mass increases, boiling point temperature increases because we go carbon, silicon, germanium, tin. We get heavier as we go down, right? But that's the only graph that kind of follows that trend. So what we see here for these other groups, water, HF, and ammonia, as we go down our group, as we go from NH3 to PH3, as we go down that group 5 group, we see the lightest element actually has the highest boiling point temperature, but then it goes down and then it starts to creep back up. So the idea is, well, what's going on here, right? this trend is true, that molar mass increases, IMF increases. It's true except for those three compounds right there. So what is going on? This gives us our third intermolecular force. Our third one that explains these anomalous, high boiling points for water, HF, and NH3. All right? So there's another dominating IMF that's present, and that is a hydrogen bond. So a hydrogen bond has very specific criteria. A hydrogen bond is super strong. Basically what it is a special case dipole-dipole attraction that's just really, really strong, right? And it has very special criteria. And so a hydrogen bond is, again, just a very, very strong dipole-dipole attraction, and it has two specific criteria, two requirements. In order to hydrogen bond, you have to have a hydrogen present, all right? So a hydrogen has to be bonded, but it can't just be any hydrogen. It has to be a hydrogen that's covalently bonded to a very polar atom, all right? It can't just be any hydrogen. It's a hydrogen bonded to a very polar atom. And so those atoms include oxygen, nitrogen, and fluorine. So that is what explains that weirdness. Up here, hydrogen bonding is going on, and that is what is producing this abnormally high boiling points for these low molecular weight compounds, all right? So highly polar atoms, so oxygen, nitrogen, fluorine, right? And then the second criteria is that there has to be a lone pair of electrons on that electronegative atom. So you want to see an oxygen with a lone pair, a nitrogen with a lone pair, or a fluorine with a lone pair. So these are essentially, these types of groups are what you're looking for, all right? You're looking for an oxygen bound to a hydrogen, a nitrogen bound to a hydrogen with those lone pairs, or fluorine bound to a hydrogen. So if you have those groups, any one of those groups present in a molecule, then you fit the criteria for hydrogen bonding. So it can't just be any hydrogen. It has to be hydrogen attached to oxygen, nitrogen, or fluorine, and there has to be a lone pair present, right? So this is the attraction that's going on, and why it's this hydrogen bond is just a special case dipole attraction. So here's so water is kind of the prototypical case of hydrogen bonding. Water has a hydrogen attached to a very electronegative oxygen. So electronegative atoms attract electrons to it. So when we have hydrogen bonded to oxygen, what we create is this very, very polar bond where this oxygen essentially robs up, this is the wrong way, this arrow is going the wrong way. This oxygen is robbing all of the electron density away from that hydrogen atom. And so we produce a very, very positive charge, very positive partial charge on that hydrogen atom. And so if this hydrogen is very positively charged, then a lone pair on a neighboring molecule is very attracted to that hydrogen. The lone pair is literally negative charged electrons. And so those electrons will be very attracted to that very electropositive hydrogen atom. Again, it can't be any hydrogen atom. It has to be a very electropositive hydrogen atom that's made by bonding hydrogen to a very electronegative atom like oxygen, nitrogen, or fluorine. All right, so hydrogen bonding is one of the strongest IMFs, right? So in this example, hydrogen bonding is happening in different molecules, but for really big complex molecules, you can actually have hydrogen bonding in the same molecule if the molecule's big enough. And so this is called intramolecular hydrogen bonding. And that's actually what explains why a lot of like proteins, DNA folding, all of that things, like what are the different kind of protein shapes? There's like beta pleated sheets. What else is there? Guys, I haven't taken bio in like 15 years. There's the like swirly one, right? The helixes, okay? There's the beta pleated sheets, and then what else? No, there's no other ones? What is it? I can't, everyone's coughing. So the tertiary structure, right, of proteins. So that is actually explained what different types of shapes we can get is actually through the different places we can hydrogen bond. So when hydrogen bonding happens in proteins, it allows for that tertiary structure to take over, and that's why we see the different shapes that we see. That proteins fold in a certain way because of hydrogen bonding, right? Not just because you memorized it from a textbook. No, it's where the hydrogen bonding essentially puts a pin in it, right? It folds the protein and puts a pin in it because that hydrogen bond is quite strong to hold those two sides together, right? So what's this? Hydrogen bonding is almost 15% of the strength of a covalent bond. It's weaker, but that's still really, really strong. It's actually what holds those DNA strands together, where you take two RNA strands and make a DNA strand. You know, like those, what are those different like pairs, like yeah, the base pairs. Yeah, so you memorize those, right, for biology, those base pairs. What's one of them? Adenine, and what goes with what? Thymine. Yeah, so we like remember the letters, right? A goes with T. A goes with T. What goes with, and then what's the other one? Guanine, cytosine. G goes with C. And so you just memorize that, right? Why does A go with T? It's because the hydrogen bondings link up in a certain way, so only those two go together. Why does G go with C? Because there's 3 hydrogen bonds that come together and they only link up in that way, all right? So it's not all about memorization. There's a chemical reasoning why U goes with T or whatever, all right? So that's hydrogen bonding. So the criteria to look for, hydrogen attached to oxygen, nitrogen, or fluorine. So for the most part, for biological systems, it's going to be hydrogen attached to oxygen or nitrogen. That's going to be the main one, right? And so let's look at an example. So here we have 2 isomers, propanol and methyl ether. We have 2 different boiling point temperatures, so propanol and ether. Just based upon those boiling point temperatures, which substance, the propanol or the ether, has more IMFs present? Which one? Just based upon the boiling point. Propanol, yes. Higher boiling point temperature means more IMFs present. So hopefully you see where this is going. One compound can hydrogen bond and the other one cannot. So if we look at these 2 compounds, can they both do London dispersion? Yeah, because everything has London dispersion. Are they both polar molecules? Can they both dipole-dipole? Yes, and I try to show you that. See how there's this oxygen molecule in it breaking the symmetry? And I tried to show it to you with that arrow. So both of them are polar molecules. They can both dipole-dipole. So hopefully you can see the last criteria. Which one can hydrogen bond? Propanol or ether? Propanol, because here we have, in propanol, there's the electronegative oxygen bonded to hydrogen. So you might think, oh, but ether has oxygen, but is that oxygen bonded to any hydrogens? No, it's not. So there are no electropositive hydrogens that can actually participate in that ether molecule. And this is what explains the low boiling point. Ether only has 2 of the 3 IMFs present. Okay, so let's look at one more. Which of these substances can participate in hydrogen bonding with itself? So I have ammonia and ammonium, and I already drew the Lewis structures for you. I drew all the lone pairs, right? So remember the criteria for hydrogen bonding. It's a hydrogen bonded to oxygen, nitrogen, or fluorine. So do both of these compounds agree with that? The nitrogen part, yeah, but what's the second criteria? Lone pair. So which one of these can participate in hydrogen bonding? Or can both of them do it? No, it's only one of them. So only ammonia can hydrogen bond because ammonium, NH4 plus, has no lone pairs. So ammonium cannot do hydrogen bonding. You might think, oh, but there's an electropositive hydrogen. Yes, that's true, but there's no lone pairs, so we can't, there's no lone pairs on another ammonium floating around to make that attraction. So in this case, only ammonia can hydrogen bond with itself. Okay, all right, so there's our hydrogen bonding. Okay, one more conceptual thing. Which picture correctly identifies the hydrogen bonding in a mixture of water and hydrogen gas. So this is what water looks like. And then hydrogen gases just looks like that, right? So remember, when we talk about a hydrogen bond, we're always talking about electropositive hydrogen interacting with like a lone pair, something else that's electronegative, right? That's a hydrogen bond. So which one of these pictures is correctly showing that hydrogen bond interaction? A, B, or C? So take a second, think about it, and then talk to someone around you whether A, B, or C is correctly depicting a hydrogen bond attraction. A, B, or C? Okay, so I'll go through the wrong ones first. Why is B not correct? What is B circling? B is circling bonds. What is this chapter called? Intermolecular forces. Yes, so B is just circling the covalent bonds that we learned about in chapter 8 and 9. So B is not correct, right? Because these are bonds. These are actually bonds. We're looking at interactions between a water molecule and another water molecule, but it has to be a hydrogen bond. Okay, so of A and C, which one is interacting or is depicting hydrogen bonds? A or C? What do we think? C, yeah. So remember the criteria for hydrogen bonds. It's a electropositive hydrogen attracted to something else that's partially negative. So let's look at A and think about why that one's not correct. So A, you might be thinking, oh, but hydrogen, look, that's a hydrogen attracted to an oxygen. That's a hydrogen attracted to an oxygen. So oxygen is partially negative because it's on that water molecule, but it's bonding to this hydrogen. This hydrogen is on what kind of molecule? On an H2 molecule. So is this hydrogen partially positive? No, this is a nonpolar H2 molecule. So this is actually not a hydrogen bond. So remember when I said just because a hydrogen is present doesn't mean it can hydrogen bond. And that's an example of this, that yes, there's a hydrogen present, but that hydrogen is not electropositive enough to actually participate in hydrogen bonding. Yeah. Okay, yeah, so intermolecular forces means that it's a molecule interacting with another molecule. So in these pictures, I have like multiple waters, multiple hydrogens, whatever, depicted. I got lazy in these ones. I just said which substance can hydrogen bond with itself. Meaning that when you have a sample of ammonia, it's not just one ammonia molecule. You actually have a million of them. I just got lazy and didn't want to draw a million of them in that picture. Does that make sense? So we have to, in our mind, pretend that we have a bunch of these in a box interacting with one another. You have to pretend that we have a bunch of these in a box interacting with one another, right? Because we never do we actually just have one molecule. Does that make sense? Okay, yeah, all right. Good, I know that's a good question. All right, so in A, the hydrogens that are being interacting, part of that interaction, the hydrogens are part of H2, which is a nonpolar molecule that does not participate in hydrogen bonding. So C is the correct answer. And yes, it's the one with the least amount of interactions, but that's because only water can hydrogen bond with other water molecules. Because water has that electropositive hydrogen interacting with the electronegative oxygen on a nearby water molecule. H2 cannot participate in that interaction because there's nothing electronegative or positive in that molecule at all. So C is our correct answer. So hopefully you see why. It can't just be any hydrogen. It has to be a very special case hydrogen, a hydrogen attached to an electronegative atom, and lone pairs have to be around. Right? Good? Okay, all right, so let's put it, oh wait, no, one more. Okay, the last important intermolecular forces. Okay, so we already talked about one of these, all right? Ionic attractions, or ion-ion attractions. Ions attracted to full-blown ions. This is actually just lattice energy, all right? Lattice energy is ionic attractions, where we have like a sodium plus attracted to a chloride minus. These are full-blown charges attracted to one another, right? Ionic attractions require full ions to be present. That's not part of this chapter, but I wanted to relate lattice energy to kind of what we've been talking about, ions attracted to one another, because this is related to the next intermolecular force, which is ion dipole attractions. And I want to break down this name, okay? Ion dipole, in order for ion dipole to occur in a sample, and again, this is in a sample, so we have to have a lot of different molecules present. You need two things to have ion dipole take place. You need something that's ionic, and you need something with a dipole. Those are the two things you need for ion dipole to occur. I think I have that right down here, right? You have to have an ionic substance, and you have to have something that has a dipole like water. So ion dipole is the reason why salt dissolves. So salt, NaCl, is composed of Na plus and chloride minus ions in the solid phase, where ion-ion or lattice energy takes place. But salt dissolves in water, and the reason salt dissolves in water is because of ion dipole, that the polar water molecules are strong enough to break the lattice energy of these ion dipoles, or these ion-ion attractions. So what happens when you dissolve salt in water? This is what happens. All right, here's salt, Na plus and Cl minus. The ions dissociate from one another, so we have Na plus and Cl minus, but we have also an infinite amount of water molecules present. Water is a polar molecule in itself. So when chloride is floating around in solution, chloride is negatively charged, so the positive parts of the water molecule attract itself or solvate each chloride ion. It essentially cushions that chloride ion with the positive parts of the water molecule, right? Where sodium, on the other hand, sodium's positively charged, so the negative parts of the water molecule cushion that sodium plus ion to solvate it. All right, and so this is what we call solvation. We'll talk more about this in Chem 1220, but this idea that water molecules with its permanent dipoles can come in, break up the lattice energy of the salts, fully ionizing sodium plus and chloride in that substance. So for ion dipole, what we actually want to look for, and this one's kind of weird, we want to look for salts that are dissolved in water. So you want to see something like NaCl aqueous. This has ion dipole present, right? It has to be a salt dissolved in water, so it has to be aqueous, right? But if we're just talking about NaCl solid, NaCl solid has the ions present, but there are no substances with dipoles because it's just a NaCl solid. There's no water molecules present. All right, so you have to have two things, an ionic compound, and it has to be dissolved in water. Okay, all right, so that means when we write like the full ionic equation for NaCl and we write Na plus and Cl minus, this is actually kind of not true because free sodium doesn't exist. It's always solvated by a number of water molecules around it, all right? So it's kind of not true, but it's okay. It's for simple terms, it's fine. Okay, so a kind of fun thing, and this is kind of review a little bit. Ion dipole attractions kind of can be explained by some of our solubility trends, all right? So ion dipole is a really, really strong attraction, all right? And when that attraction is really strong, it can be strong enough to break the lattice energy that holds together your ionic compound. So let's review a little bit, all right? So let's look at this table. Remember, this was from chapter 4. When did we use this table? To predict what? Solubility of salts. Yeah, so it's like if you put NaCl in water, you're predicting, oh, does NaCl aqueous, does that salt dissolve in water, right? So when a salt dissolves, that means ion dipole is happening. So if we look at this chart, it looks like a lot of these like -1 anion compounds are soluble in water, that they can ion dipole. But these insoluble ionic compounds, these compounds typically stay as a solid, don't ion dipole. So let's think about it. All right, so let's look at these different compounds: calcium chloride, iron 2 sulfide, and sodium nitrate. Which one in this little set has the poorest solubility in water? Meaning, which one's not soluble in water? So just look at the list. Which one, if you put it in water, will be a solid? It'll stay a solid. Which one? The iron one, yes, because if you look at the list, sulfide is one of the insoluble anions. Yeah, all right. So let's review chapter 8. All right, so that means that in iron sulfide, that when you put it in water, water can't produce an ion dipole strong enough to break that lattice energy that holds together iron sulfide. So let's review chapter 8. Which of these compounds possesses the largest lattice energy? So what do we have to do? Do we have to build the whole Bohr-Haber cycle to do that? No. What do we want to compare? Charges, yeah. So let's look at the charges. So calcium is +2, chloride is -1, iron is +2, -2, and then sodium nitrate is +1, -1. So which one of these has the easiest or smallest lattice energy? Smallest. Sodium nitrate. So is that easy to break apart those ions? Yeah. So waters can come in and break apart the lattice energy holding together sodium nitrate very easily. So relate that to the idea, is sodium nitrate very soluble in water? Is it, according to this table? Are nitrates soluble? Yes. And it's because it has that compound has a very low lattice energy, easily dissolved because ion dipole can come in, take over. But then which one has the largest lattice energy? Iron sulfide, the exact one we just said doesn't dissolve in water. And that's because its lattice energy is too strong for ion dipole to come in and break those ions apart. Right? So yeah, that's what we see here. When an ion is really soluble, that means the strong ion dipole attractions can break apart that lattice energy, the weak lattice energy. Versus the insoluble things means that, oh, ion dipole can't come in and break those things apart. That lattice energy is too strong. Right? So it trends a little bit differently there. So I wanted to relate it to something that you kind of already knew. All right. So that was the fourth. Ion dipole was the last criteria, the last intermolecular force, and the criteria for ion dipole is you need two things. You need a salt dissolved in water. That is how you get ion dipole. So meaning you need something that is an ion, like chloride, dissolved in water because it has a permanent dipole. Okay, so let's put it all together and, talk about all of the different IMFs that we discussed. London dispersion, dipole-dipole, hydrogen bonding, and ion dipole, right? And here's the different criteria for all of these, okay, and the requirements and the trends for all of them. London dispersion, all matter has London dispersion, but it's most important in nonpolar compounds, right? The trend is with molar mass, and then sometimes surface area, if molar masses are similar. Right. Once we start working away from nonpolar compounds and we talk about polar molecules, right, you want to look for molecules with permanent dipole moments, polar molecules, and then that trend is usually as your dipole moment increases, so the more polar your molecule, the more dipole-dipole attraction that there is. Right? The next one was hydrogen bonding. That one's a lot stronger. This is just a special case dipole-dipole. You're looking for these types of groups, meaning you have an electropositive hydrogen and electronegative atom also on in a molecule. And so the hydrogen bonding trend is, what we see is that typically HF is actually going to be the strongest hydrogen bond because it's the most largest electronegativity difference. But we'll also see water has 2 places it can hydrogen bond, so it has unusually high hydrogen bonding capability. So the more places you can hydrogen bond, typically the stronger IMFs are present. And then the last one was ion dipole. You're looking for free ions dissolved in a polar solvent, so that's something like NaCl aqueous would participate in ion dipole. And then here are some examples. I like this chart because it talks about the actual strengths of the different attractions, and you can see their relative strength difference, how much attraction is actually there. That London dispersion, the most it can have is 30 kilojoules per mole, but it's as low as 0.1 kilojoules per mole in terms of its attractions. But once we get to dipole-dipole, we see, it increases, hydrogen bonding increases even more, and then the strength, the attraction that comes from ion dipole is over 50 kilojoules per mole. That's a really strong attraction that can take over in your sample. And so this table kind of says the exact same thing that my written table shows as well, the criteria for all those different, those 4 different intermolecular attractions. Okay, so let's go through this list, and I have the Lewis structures drawn for you, and let's decide each of these compounds what IMFs are present. So let's look at water. So I have the Lewis structure for you. That'll be important. Does water have dispersion? Yes or no? Yes, because everything has dispersion. All right, next, does water have dipole-dipole? Yes. What question in your brain are you asking yourself with dipole-dipole? Is it polar? Yes, so it is. But I drew water straight. Is water linear like that? No, it's not. Just because I drew the Lewis structure that way doesn't mean it actually is linear. It is bent. Okay, hydrogen bonding. Can a hydrogen bond? Does it have the criteria? Yes, it has a hydrogen attached to an oxygen, and that oxygen has a lone pair. Okay. Can water ion dipole? So just look at the name. Ion dipole. You need something that's an ion, and you need something with a dipole. Does water have a dipole? Yes, but are there ions in water? No, there's not, so it cannot ion dipole. You need both of those things in order for ion dipole to be present. Okay, CF4. Does CF4 have dispersion? Yes, everything has dispersion. But does it have dipole-dipole? No, because CF4 is in fact a nonpolar molecule. That carbon is attached to 4 fluorines. They're all identical. It's like CH4. Right? All those fluorines cancel each other out. So this is a nonpolar compound. So once we X out dipole-dipole, if it's a nonpolar compound, you don't even have to look at any of the other ones. Okay? You can't have hydrogen bonding at all if you have a nonpolar compound. Okay, CH2F2. Does it have dispersion? Yes, everything has dispersion. All right, this one's tougher. Does it dipole-dipole? So ask yourself, is this polar or nonpolar? Think very carefully. Is it polar or nonpolar? What do we think? It is polar, yes. It is very polar, yes. Because is this molecule, is it flat? No, it's not. It looks like it's nonpolar. I tricked you. I drew it where the 2 fluorines and the 2 hydrogens, it looks like they cancel each other out. But are those bonds actually 90 degrees? They're not. This molecule is actually a tetrahedron. All right, so I put a fluorine there and a fluorine there, like that. Now tell me, if I drew it this way, is that nonpolar? That can never be nonpolar, no. It actually looks just like water, doesn't it? Actually, if you look at these 2 examples, water and the CH2F2 example, these 2, they both have the same electron geometry, right? It's just like I drew them different. Instead of lone pairs, it's just like 2 hydrogens instead. So they actually have the exact same polarity. Both of them are polar molecules. All right, can this molecule hydrogen bond though? No, but there's hydrogens there, and there's fluorines there. There's hydrogens and fluorines, and it can't hydrogen bond, but I thought that was allowed. They're not bonded to one another, right? The hydrogen's not bonded to one another. Just because there's a hydrogen present and a fluorine present, they have to be bonded to one another, so this one can't. All right, okay, C3H8, so this is propane, I think. So all those lines are hydrogen atoms. Is there dispersion? Yes. Is there dipole-dipole? No. Yep. So all those carbons, hydrogens, nothing's polar in that molecule. Okay. What about this molecule? So this is an ether. So it's oxygen bonded to, instead of hydrogens, it's 2 methyl groups. Right? Does this have dispersion? Yes. Does it have dipole-dipole? Yes, because basically this molecule looks like water. It's just instead of the hydrogens, you replaced it with a carbon instead. But is it exactly like water? Can it participate in hydrogen bonding? No. But there's hydrogens and an oxygen present. But what's the problem? They're not bonded to one another. Yeah, so this one cannot hydrogen bond. Okay, and then the last one, NaCl aqueous. We have sodium pluses, chloride minuses, waters that have permanent dipoles. Is dispersion present? Yes, everything has dispersion. Dipole-dipole is happening in the water separately, because this is a mixture. This one's weird because we have 2 things present. We have Na plus, Cl minus, and we have chloride. Hydrogen bonding is happening in the water, but between the NaCl, or the Na plus, and the water molecules, ion dipole is happening, because we have ions coming from sodium and chloride, and then we have the dipole coming from water itself. All right, so that is the list. So a lot of this boils down to chapter 8 and 9 ideas, Lewis structures. Yeah? Does it? So here's the thing. Hydrogen bonding doesn't happen between chloride and water. Hydrogen bonding happens in the water. So if we look at this list up here, all right, it says ionic solids dissolved in polar liquids only have dispersion and ion dipole attractions. Those are the attractions happening between the sodium chloride and the water. Those are the only things that can happen. The ionic compounds, they have like ionic attractions. The water molecules with itself have hydrogen bonding and dipole-dipole, but you won't see those attractions between the salts and the water. So I'm taking a hint from this table here. All right. So that's why I didn't circle them, but there is those attractions in the water part of the sample. Okay, so I think 2 more slides. So which of these pairs possess the higher boiling point temperature? So what are we looking for? The sample with more IMFs. Yes, we're looking for the sample with more IMFs. So which one possesses the higher boiling point temperature? Water or ethanol? What do you think? So let's think about it. Do they both have LDF? Yes, they do. Do they both have dipole-dipole? Yes, they do. Can they both hydrogen bond? Yes, but what's the difference? One has 2 of them, and then the other has 1 of them. Yes. So since this water can hydrogen bond twice, ethanol can only hydrogen bond once, which one do you think has more IMFs? Water. Yes, water. Okay. These 2 molecules. Which one has the higher boiling point temperature? So ask yourself, do they both have LDF? Yes. Do they both have dipole-dipole? No, they don't. They don't. One of these molecules is polar, the other one is not. So this molecule, trans 1,2-dichloroethene, is what, polar or nonpolar? This one's nonpolar, yeah, because this chlorine's going that way, this one's going that way, those two vectors cancel. So this is a nonpolar compound. So then which one has the higher boiling point? Trans or cis? Cis, yeah, because in this one, both the arrows are going in the same direction, so you have a net dipole in one direction. So this is a polar molecule. All right, finally, bromine or xenon? Bromine or xenon? So let me give you the molar masses. Bromine has a molar mass of like 160, and xenon is 131 grams per mole. So you might be thinking, oh, they both have London dispersion, right? Can either of them dipole-dipole? No. So we're just looking at London dispersion. What are the criterias for London dispersion? Molar mass and surface area. So the idea is when molar masses are similar, sometimes you have to look at surface area. Because if you look at these, you might think, oh, bromine is a lot heavier. Oh, I didn't write xenon. Oh, yeah, it is. Okay. Bromine is heavier. Oh, and it actually has more surface area because a diatomic particle, right, is more kind of linearly shaped here, and bromine is heavier. So our answer would be bromine has the higher boiling point temperature in this example because its molar mass is heavier, but and it has more surface area. Yeah. We would never give you that example. There's actually one. I was wondering if it was this one. What about this? Which one do you think? See, I'm trying to make ones that are really similar. So if we wanted to do argon and diatomic fluorine, argon has a molar mass of 40 grams per mole, and fluorine's is 38 grams per mole. Which one do you think has the higher boiling point temperature, argon or fluorine? Fluorine. Why? Is it because of molar mass? No, it's because of surface area, because I try to pick examples where the molar masses are basically the same. 40 and 38 are basically the same. All right. So what we're going to actually look at here is surface area. Yeah. So we try to make it obvious. We won't give you trick ones that you need to know. But what I could ask you is I could give you these two compounds. I could say argon and fluorine, here are their boiling point temperatures. What explains their boiling point temperatures? And one of those options would be molar mass, but you should recognize, oh, the molar masses are so similar, that's not what explains the difference. That's how we would approach a question like that. Okay, so we talked about boiling point temperatures, and so this is the last slide I wanted to talk about, and that's other trends that we can get with relative intermolecular forces. Intermolecular forces are attractions molecules have to one another. So I like to think of it as the molecules in a sample, they're hugging one another. So if they're hugging one another, is it easy or hard to make them boil? Hard, yeah, because boiling, you rip them apart, right? And so if you keep that idea in mind, a lot of these trends make sense, all right? So one of the other trends is as intermolecular forces increase, viscosity increases. So viscosity is how slow something pours out of like a cup, right? So like water has so water isn't very viscous, but like something like honey or maple syrup is very viscous. Right, it pours very slowly. So I like to think of it like this. If the molecules are very attracted to one another, they're not gonna let their friends like get poured out of a glass. They're all holding on to each other so tight that they pour out slowly, right? So what you see here is viscosity. Viscosity, let's see, here are different viscosities of hydrocarbons, and you see as they get heavier, viscosity does increase, right? And so something that happens also with viscosity is that viscosity decreases with increasing temperature. So if you think about it, you know, like if you have maple syrup and you want to put some on your pancakes in the morning, but it's pouring, if you like take your maple syrup out of the fridge and it pours very slowly, Oftentimes what you can do is just pop it in the microwave for like 30 seconds to warm it up, so then it pours out faster and it's more tasty. And so there's actually a chemical reason for that too. If we put something in the microwave, what are we trying to do? Increase the temperature, but we understand that increasing the temperature actually increases the average kinetic energy of your sample. So if we heat up our sample, your particles are moving a little bit faster, all right? They're vibrating a little bit. So when you think about viscosity and the slowness of the pour, the more kinetic energy that's present, those molecules will break away freer and will pour more quickly out of that container. All right, so that's viscosity. And then the last IMF we'll talk about here is surface tension. So the trend is as IMF increases, surface tension also increases for a sample. All right, so what surface tension is if you think about a sample, this is a bunch of molecules, all right? There's actually differences in attractions in the bulk of the sample versus the surface. So if we look at this molecule right there, and think about the IMFs that this molecule is experiencing. This molecule is equally attracted to all sides of it. So you can think, oh, all of its attractions cancel out with one another. If you think about it in terms of vectors, it's attracted to a molecule above, below, side, and side. Right? There's this equal attraction in the bulk of the sample. That's not what's important to surface area, surface tension. Surface tension is actually most important at the surface. There's different attractions going on. Here, this molecule, does it experience attractions on all sides of it? No, it's missing this piece. So this molecule at the surface has attractions, to the left, to the right, and a net pointing down, so this way, all right? Where it's this net downward force is due to the missing attraction up here. And so what happens is this is why droplets form on like water, because of the surface area. You're missing this attraction on the outside of the surface of your system. And so the extent of surface area increases as the intermolecular forces of your entire sample increase. So that's the trend. As IMF increases, surface tension increases, and viscosity increases, all right? Okay, so that's IMFs. All right, and so that kind of puts together chapters 8, 9, and putting them into ways that we can observe all of the different Lewis structures and us interpreting, electron molecular geometries, putting them into things, properties we can actually observe in lab. If you ever think, why is water liquid at room temperature? It's because of the IMFs that are present in that sample. Okay, so we'll stop right there and we'll do some review.